Okay, what I was telling you that we have completed about the current mirrors and about all the things. Now we need to study about the what is the basically a voltage or the current references basically. Okay, for that case, what we required that is what um, here I mentioned that the voltage or the current references. Okay, requirement of the reference circuit should be independent of the power supply. That is the first requirement, and it should be independent of the temperature. It means if any kind of a temperature increasing or decreasing, the referentials should not be going to be changed, and it should be independent of processing variation. Processing variation means you can say a process parameter like beta and IBO. Okay, these all things it should not be depend. It should be independent of that. These all things. And the last one is that it should be independent of the noise. We have already seen that how we can cancel out by utilizing a different mode of things. Basically, CMRR, we have seen how we are basically when we are having a differential input, then we basically reject that noise by utilizing that one. So these are the requirement for the voltage and current references. So what should be the sensitivity if I'm going to talk about, then it will be going to be depending on what is the basically the supply voltage, okay, and what is minute change is going to be occur, and due to that one what the reference current is going to be changed. If it is this is comes to be nearly one, it means the system is very good one, otherwise we need to refine it again. That is what written. If it is equal to 1, then 10% change in the VDD result in a 10% change in the references also. If it is working like then it will be properly working. It means it should be always nearby 1. Now let's check about the simple bias circuit. Simple bias circuit, this is nothing but when you are going to apply a voltage divider rule. So this is basically a typical potentiometer. Okay, how we are going to find out the voltage here? That is, if I'm going to write a voltage across this one, oh here, voltage across this one, what we are going to say, what we are going to write it here? Anybody can tell me? So basically the resistance, depending on this resistance, 1 and 2, we can directly write this value. That is nothing but R2 by R1 plus R2 into VDD. So basically this is the voltage. So this is what we say, this is nothing but a reference voltage, and depending on the what is the resistance in between this part will going to decide our basically the voltage at this particular point. So this is a one of the you can say example for that one, or you can say from which we can define our stability, how we can define. So basically if I'm going to say here the VDD is going to be reference for that one, where the VDD is going to be changed, then only that stability is going to occur, going to be changed this value. So basically this can be designed with the transistor based resistive divider by same way. What is that? If VDD is applied here and we are just connecting this terminal of that one and and it is crossing across this one, so it is also similar behaving like that one, because if I'm going to say if it is connected to this one, it is nothing but it behave like a resistor, and similarly for the case of this one, this is also behave like a resistor. So what is going to happen? The resistor across this one, resistor across this one, and resistor across this one going to decide our V out. So this is nothing but a replica of this thing. Okay, this is how we basically design a transistor based resistive divider. So when we are going to talk about that one, that for the case of PMOS and NMOS, if I'm saying Kn is equal to Kpn and it's a threshold voltage assumed to be 1, then with that case only we can assume that our stability is going to be comes to be 1. This is how we basically do the calculation. Although what is going to happen, it is going to have a poor power supply rejection. Why it is going to say like that? Poor power supply rejection. We'll see that one. Now see. Now comes to the comes to the MOSFET source. So now what we have done it, what just this part we have changed it for not to have a power supply rejection. Then what are we going to do? Simply we have taken a one this here. So what is going to happen now? This resistor is going to be working similar like that one now, and this is what we have taken a kind of a current source. Basically, you can say on the basis of this two resistors, basically this and this, it is going to drive our output current. It is similar like what you have seen in the current mirror basically. So this is how basically works. So this is one nothing but a bias circuit involving diodes. So why it is called to be diode? Basically, the circuit here, it is behaving like a resistor, and and that diode also you can say are simply are behaving like a resistor depending on the voltages. So if we say like that one, we can replace this particular circuit with the help of the BJT and saying this thing to have another BJT source. So this is nothing but a replica in the form of the BJT source. And here it is a MOSFET source, and this will be called as a BJT source. But when we are do like this one, that time we are having a significant power supply rejection, higher PSRR will going to become that we wanted to do. Now comes to the BJT source in a small signal model. So basically, if I'm going to look around this one, this is in the small signal model. What is going to happen? This is behaving like a resistor, and whose resistance is nothing but 1 by GM. That is a 1 by transconductance. So basically, this is nothing but what from the beginning, from where we have started. See, so we have started from here. So when we are just looking into that picture, we have come to that particular that thing. So that is what we have designed that one. And now this is what going to have a voltage output voltage sensitivity we can earn. So now if I'm going to calculate, that is what Vref, that is this one, that is nothing but VDD by 1 plus GM R. Okay, that is by with the help of a voltage divider rule. Now if I'm going to evaluate the transconductance, we'll get this value where the UT is nothing but a threshold voltage. Now further on, if we want to find out stability in respect to the VDD, so that is a basically formula we will going to find out. With the help of this one, we can find out the output voltage sensitivity. Just do the mathematics. This is you are going to get it basically how we are doing. Just you can see this part. So if I'm going to want to find out the VDD nothing but what is that? VD is going to be refers to as this one. By the voltage divider rule, we can find out this thing. Okay. So VDD here, when we are assuming this part also, then we're going to have this thing. So if I'm going to divide these things, we will get a stability factor with respect to VDD. That is nothing but going to become this one. So this is what we wanted. So we have already obtained this thing. So assuming that VDD minus Vref is much greater than the threshold voltage, then this is going to be comes to this end. That is all the mathematics only. And if it is so, if you look into this one, if you're look into this one, as we are saying, this is a very high. Okay, since this Vref is nothing but at the 0 point, what is going to happen? This is nothing but it is also going to be VDD 0 only. So that is why it is going to be have a one value, and so totally that our stability is going to depend on the threshold voltage and the V reference only. So basically, these are the mathematics. I'm not going to go into more detail in that one. So for that, this basically BJT source type of system, we basically obtain a stability factor going to become like this one. Okay, where it is to be 4% only. Now, bias circuit involving diode. This basically this configuration is going to be allow a wider variation of output voltage, which also going to be increase your significant power supply rejection. So that is what this is the different circuits we be basically uh, going to see this type of things basically. Rather, rather we are not doing directly connection. We basically connect this thing with the help of a two resistor. So basically, this is nothing but going to give you a variation of the voltage, output voltage, depending on this R1 and R2, or rather only depending on this resistance and this whole resistor. So this will increase our more power supply rejection. So this is what the breakdown diode referencing. So when we are going to look into this characteristic, IV characteristic, that we can see it here as the this is there. You can see as we increasing that after the breakdown, it is going to have a high current. Okay, so this is what going to happen. And similarly, if I'm going to check out this diode referencing on the basis of temperature, you will get this kind of a variation. Okay, these are all the basically mathematics. Okay, depending on that previous sensitivity value, so stability factor, basically we can see it here. On the basis of that when we have all calculated that parts. So this is the what we are going to have, what we are going to see it here, that we are getting a very noisy output voltage for that case. So that's why we go into the bootstrap referencing. Bootstrap referencing, basically what is that? Rather we are utilizing that part only. We look into this picture also. So now what is happening now? Now we're going to look into that gain of that one, that is going to be depending on the W by L ratio of the I1 and I2, that is this one and this two. So and in the sub threshold or the BJT, in the case of BJT also we're going to see that one. So if I'm going to calculate the V here, this one, that is nothing but the VTLN AI, that is this part, that is nothing but equal to IREF R. IREF R, because this is current which is going to flow through this one, because uh, we already know that IDN current passing through the this MOSFET is going to go through that resistance. So basically, we can calculate this in this form. So if I'm going to evaluate this thing, we can get the IRF this thing. So if we get that one, so we can replicate that part. We can run another these MOSFET on the basis of this particular bootstrapping. Basically, we try to replicate referencing the parts of the current. So that is what we try to replicate that thing. So if we are going to connect with this with another this PMOS and this is NMOS, then we can get a two different referencing points. So now for the boot bootstrap referencing, that is what this is what the part, and this will generate a current, and this current is nothing going to be passed through another. This is the external circuit what we are talking about. So now we can utilize anywhere that referencing basically. Depending on that one, we have also seen that calculate the I1 and I2 current, depending on that what we have gone through this one. So these are the different starter circuit bootstrap referencing. So that is what all the voltage or the current referencing part of that one. So these all I've given in this PPT. I will share this thing with you. Now comes to the basically what is that op-amp. Okay, that is all of the current and the voltage referencing part. Now comes to the basically what is that op-amp. I'm going into that one. Okay. Now simply if I'm going to talk about the operational amplifier basically what able to do a kind of a operation like addition, subtraction, or all the type of thing basically. That is why it is called as a operational, and it is going to amplify that part which we are doing that kind of a with different type of that operation. That is why it is called as a operational amplifier. So basically its structure is like that one, which is having a two input and an output, and its output is basically depending on the our saturation voltage, but that is nothing but a supply voltage, that is it is rolling out in between the plus V set and the minus V set. Okay, so if we want a distortion less type of amplification, then we should to constrain our input voltage in between, that is the V minus V set by open loop gain and the V set by the open loop gain. If it is going to become, then only what is going to have our op-amp is going to give you a distortion less amplification. Let's check about that one, how it is going to happen. Now before that one, we need to know this is the plus side will be a non-inverting terminal and the negative side will be a inverting type of uh, terminal, and this is what VID is nothing but a difference voltage which is applied over this input side. So basically this is nothing but a VA minus VB. So it should be in between these two constants. So now look into this one. Let's say, assuming that we are having a open loop gain that is 10 to the power 4, and we are having a supply voltage rolling in between a plus minus 15 volt. So if you are going to look into this one and we are giving the input like this one, so if I'm going to see what should be the value for the output, it should become what? It should be going to come in between. This should be a 16 voltage and this should be minus 16 voltage. Okay. But what is saying? This should be in between plus minus 15 volts. So that is what I have mentioned here. See it here. After this part, this is cut it down. So basically that is what called as a distortion. This is what called a distortion. So for avoiding this part, we need to have this input voltage. It should be in between this range. That's the mean of that one when we are dealing with the operational amplifier. If it is not that, then it is going to have a distortion type of a output. So we need to take care whenever you're utilizing a operational amplifier. So when you are going to talk about the open loop gain, this is the basically ideal characteristic of ideal op-amp. It should be have a high open loop gain, or you can say an infinite open loop gain. What the mean of it? If the inverting or non-inverting, if I say here we have already seen this is nothing but a we are saying a non-inverting terminal and B we are saying a inverting terminal. So if we so, it means that if we are having a VA greater than VB, that is a non-inverting terminal is having voltage greater than the VB, then it is going to give you a plus V set. Basically, when we are just treating as a there is no feedback. Basically, without feedback, op-amp is nothing but a comparative type of a comparative amplifier. Basically, so any of the voltage is going to increase, that side it will going to roll out that result. Basically, when we are saying a non-inverting terminal is higher than the inverting terminal, that time it is going to give you a plus V side. And whenever that non-inverting terminal is less than the inverting terminal, that time we are going to get a minus V side. Okay, it means if it is so, so whatever is going to come, that will give you the tangential form which is coming across this one. It is nothing but going to have a 90-degree. Okay, that is what the mean of saying this thing. If the 90-degree is not there, it means it is not going to behave like a this ideal op-amp. So in a practical, definitely we are not achieving this, basically this type of things, until we are not utilizing more than the 10,000 or more than a 10,000 open loop gain. So basically, that the mean of things. If our op-amp having a infinite gain, that is what basically say, then that time we are going to get the output like this one. Now, check about the equivalent circuit of the op-amp operational amplifier, that is, which is saying that for the ideal case, input impedance is very high, that is a infinite, and output impedance is very low, that is a zero. Okay, and the differential input is going to have a output with the open loop gain with the this one. So this is the equivalent circuit of the op-amp. So it means we can directly replace this part as a this one, or you can say indirectly connected input terminals, and this is what basically represented with the short circuit. Basically, this is what the equivalent circuit of the operational amplifier. Now check about the non-inverting amplifier. Basically, so whenever we are going to say we are going to have a feedback across the negative feedback, and we are giving a the voltage at the non-inverting terminal, that time it is going to be called as a non-inverting amplifier. And I'm not going to go into more detail in this one, but because this is a very basic part. So whenever the open loop gain is a finite, that time this is nothing but we are going to get this exact gain, closed loop gain. So, but when we are having an infinite, we're going to get achieve this for the case of a non-inverting amplifier. So I'm not going to go into detail of virtual short and a virtual ground. This is already well-known factor which we have already seen in the previous standards. Basically, in the second year or third year, we have already gone through that one. So I'm not going to explain about the virtual short, virtual ground concept. So now look into the inverting terminal. This is also what when we are having a voltage at the inverting terminal, and the feedback is also at the inverting terminal. So that is what that case going to have a whenever we are having a finite type of a open loop gain. That time we utilize this formula, and if it is so, if I am having an infinite open loop gain, then this is going to come. Okay, this is all about or which we already know. Now comes to the our research point of a view, what we do basically. Now comes to the research point of view. I'm going for in the at the beginning of this PPD. Now we have already seen that what is the general purpose of things for the open things. Now let's see what are the basic things. What is the performance parameters? That is, first one is what we are going to see, that is a gain. Okay, let's have an example. So this is already that what is it? this is that is a feedback network, that is with the negative feedback network. That time only that what is going to happen, our gain is going to be increased. Basically it is going to stabilize the gain basically. So which, if you are going to look into this one, if we are going to assume that the our for the design of a nominal of a 10 gain, we basically say 1 plus r1 by r2 is equal to 10. Then if you are going to look into the closed loop gain, so what is going to happen? So here we already know this formula. Okay, so we try to deduce in the form of this part. Basically this part we want to deduce, and if we do so, and we, if we divide this a1 with the this below denominator part with the a1, we're going to achieve that. What is that? We are going to achieve a part, this part. Basically this part I'm going to say, that is going to have a 1 by r1 by r2 plus 1 by a1 plus 1 basically. Okay, so by Bernoulli's we can write this part into this way. Okay, if we do so, we can achieve this one. And Bernoulli's only happens when we say this part is very high, a1 is very high, so we have represented in this one. So if we do so, what is going to happen? We can again we can achieve a error. We can calculate the error, and that error is going to come to be 1% when we are having a that gain is greater than 1000. So which it is our basically advantageous whenever our gain is very high for the op amp. Okay, but what is going to happen if we design a amplifier with the help of a common source? Okay, rather say common source, we can say in a MOS technology. What is going to happen if we say do so amplifier we are making in the form of the MOS? Then what is going to happen? With the help of a common source we design it, and in that case we require this part for the having a nominal of 10, that is has to be done. But however we cannot achieve the 1% only error. We cannot guarantee it about that one. So why? Because the variation in the mobility and the grid oxide thickness of the resistor and the value of the resistor typically, and an error greater than the 20% basically we achieve. Basically we are obtaining. So it is not a very good thing. Although we need to find out what is the other way to evaluate these things. So we're going to see after going through the performance parameters. So if you're going to look into the second performance parameter, that is the small signal bandwidth. So after a 3 dB cutoff, what is going to happen? Until that one, we are achieving the unity gain. After that, it is going to roll off. That is going to happen. That is, and the case of a large signal bandwidth, what is going to happen? Since we have already seen that it is not going to have a, in a practical way, we don't have any kind of a exactly what we want. There's a kind of a delay is occurring because of some internal capacitance and parameters. So that time we are achieving the output in this roll off way. So that is what basically happening in the case of a large signal bandwidth, and that is what nothing but decided by the slew rate, basically how it is quicker the op amp it is. Although for the case of the IDM it is a very high, or you can say infinite, but in the case of a practical circuit it is not that much. Basically it says how the output is changing with the respect to the in the form of the microsecond. Basically we check it out in the slew rate case. Now comes to the fourth one, output swing. Most system employing operation amplifier require a large voltage swing. It means we want us that op amp it should have a basically working in a very large uh, voltage range basically. So that is what we wanted. So to accommodate a wide range of amplitude, basically that is what the we wanted output swing. So linearity, that op amp here this is the circuit which is given here. This is also a kind of a operational amplifier basically when we are designing using a MOS technology, using a CMOS technology basically. Okay. So linearity, that is open loop op-amp suffer from a substantially non-linearity coming because of that. If you're going to look into the input pair, that is M1 and M2 input pair, this is M1 and M2, that is nothing but differential input part where it accommodated. So between the differential drain current and input voltage. In many feedback circuit, the linearity requirement rather than the gain error requirement governs the choice of the open loop gain. So that is also basically we can choose accordingly how we are going to design our uh, amplifiers. Now, sixth one is the noise and offset. The input noise and offset of the op-amp determine the minimum signal level that can be processed with the reasonable quality. The seventh thing is the supply rejection, what we have already seen in the previous slides. Op-amps are often employed in a mixed signal system and sometimes connected to the noise digital supply line. Thus, the performance of op-amp in the presence of the supply noise is quite important. For the reason fully differential topology is are preferred. We have already seen in the case of our differential topology, we are seeing that there is a common mode rejection is there basically. Now comes to this is the basic part. First one is the one stage op-amp. One stage op-amp means basically shown it here. That is a simple op-amp technology what we are talking about till now. First is the differential input. You can see the differential input is there and single output, single ended output. So you can see single ended output. In the case of differential input, differential input and differential output, you can see this part and this part. This is the differential input we have given and differential output. This is what we have seen. For this case, what we see, the low frequency gain that is going to come depending on the output resistance of the N type of MOSFET or a P type of a MOSFET. You can see that here the topology is basically utilizing this thing. So basically that is why we say depending on the it is going to come in a parallel to each other. That is what. In general, this value hardly exceeds a 10 in micro sub-micron devices with a typical current level. The bandwidth usually determines the load capacitance. That is here, this, and this part. The circuit suffer from a noise contribution from M1 to M4 because each having some different type of a parasitic capacitance and several internal parameters which makes to govern to go into a noise sufferer. So in all op-amp topology, at least 4 devices contribute the input noise and 2 input transistor and 2 load transistor, basically including that one, all 4 devices. Now comes to the unity gain buffer based on that basically that one state amplifier. So if I'm going to look into the input common mode voltage range, okay, for the case of this part, that is a VCSS. We are talking about this op-amp basically, operational amplifier. So if I'm going to look into V in minimum, that is V in minimum plus VGS. That is only, that is the gate. So VGS, okay, VGS was. So, and the second one is maximum. What could be the maximum? That is nothing but the VDD minus VGS3 plus VTH. Okay, minus VGS. Why I'm saying because it is a PMOS type of system. That is why we have written like this one. So this is what the basically input ranges. So if each device has a threshold voltage of 0.7 volt and an overdrive voltage of 0.3, then V in minimum, this part is going to be have a 1.3 voltage and V in maximum will be this part basically going to become a 2.1 voltage. Thus the input common mode range equals to 1.4 within the 3 voltage supply. That is going to be come basically. And in the case of that one, what is going to happen for the case of output impedance? Output impedance is going to comes to be this one. We already know that for the case of open loop, sorry, for the open loop, I'm saying closed loop system, it is going to be divided by always 1 plus beta AV. That is where the A is nothing but a open loop gain. Okay, so this is nothing but this factor is also called as desensitivity. So when we are going to talk about the output, it is going to be divided by basically desensitivity factor. So if I'm going to calculate this part, it is going to become, as we have already seen in the previous slide, it is going to have a output resistance will going to have a ROP parallel to RON and divided by 1 plus GM ROP parallel RON. Okay, if it is so, we're going to have equally this part, because what is going to happen? This is a very minimum value. That is why we say the closed loop output impedance is relatively independent of the open loop output impedance. Because of that one, we are achieving this part, allowing us to design a high gain op-amp by increasing the open loop output impedance while still achieving a relatively low close output impedance. That is what the things, because this is out of this doesn't have a containing this R0P or an R0N. That is why we say like that one. Now comes to the telescope cascode op-amp amplifier. In order to achieve a high gain, the differential cascode topology can be used. Now we want to achieve a more high gain, so that is why we cascode the circuit. Basically, this is what we are saying. So we have cascaded up this part. Okay. In that case, low frequency gain is going to come to be this one. If you are going to calculate by the help of the small signal analysis, you will get this part. But at the cost of the output swing and the adding poles basically, because as the number of the nonlinear devices increase, that number of the poles and the zeros is going to be depend on that case. Okay, so we can have this part. Basically we can bias that our system with the help of VB1, VB2, VB3. And now we are saying that our differential input going to comes to in terms of V out, but where this bias voltage is going to be change this accordingly, change the GM of this one, and basically transconductance depend on this bias voltage, that is VB3, VB2, VB1. So now we can translate that system on the basis of this VB1, VB2, VB3. So now the circuit providing a single-ended output suffer from a mirror pole at the node X, creating a stability issue. Where it is? Okay. So here I'm saying, since it is a replica, so that is why we say this thing. The circuit providing a single-ended output suffer from a mirror pole at the node X, creating a stability issue. And fully differential topology, the output swing is given by this one, where we can say ODJ of that overdrive. Basically it is the overdrive voltage of the different transistor, that is MJ. In this case, what is the drawback is there, that is shorting their input and output, that is implement a unity gain buffer. Basically it is a very difficult task to do that one. Now What is going to now see? We're going to see our output thing, that is basically our calculations. So the output thing going to be, for that case, M2 and M4. This is M2 and M4 should be in a saturation region. So for that saturation region, it should be follow this equation, that is V out should be less than or equal to Vx plus Vth. Okay, X is here. V out should be greater than Vb minus Vth4. Okay, so all together, if we go into equate the inequality, we can get this equation. For that case, we can get the voltage range is going to be come to be Vth minus Vgs4 minus Vth2. Since the op-amp attempts to force V out to be equal to the V in, for V in less than Vb minus Vth, we have basically V out going to be equal to V in. That case, only we achieve this part where it is going to have a basically a unity gain. In that case, M4 is in the triode region, while the other situation, under this condition, the open loop gain of op-amp is reduced basically. Now, if it is happening, what is going to happen as V in and V out hence exceeded the VB minus VTH4, then what is going to happen? M4 enter into the saturation and open loop gain reaches a maximum value. This is how we basically achieve our Vx minus V in. So for that case, VB minus VTH4 less, it should be less. It means you can say V in between these two ranges. In that case, what is going to happen? Both M2 and M4 are saturated, and for this one, M2 and M1 enter in a triode region, degrading the gain. Thus, the cause code op-amp is rarely used in a unity gain buffer. That is what I have already said in the previous slide, that is suffer for the case of the unity gain buffer basically. Now, designing fully differential telescope op-amp, we can design with the help of this thing, that is specification. We need to check it out, that one VDD is equal to 3 voltage and differential output thing with this one, assuming this part. Now we'll see what is going to happen for the case of the output thing and W by elevation and power budget, what is going to happen now. Let's see. For the case of current through the IM9, where the M9 is there, this is what we are going to see into. What is going to happen? That is nothing but we have already seen this part. Now we are adding this two parts only. Let's see. In that case, IBM plus IMB2 is going to have this value, and output swing, that is this one, and in that case M3 and M6 in the saturation. This is basically how we design. This is already well proved data. So this is all going to become with the help of basically a mathematics, assuming this part only. So this is how basically we design a differential telescope op-amp. And for the case of gain, you look into this one, how we are achieving. This is all basically a data, nothing else. I need not to explain this, which is already I've explained in the previous slide. Just this part only added here. Now comes to the folded cost code op-amp. Folded cost code op-amp basically nothing but going to look into this part, okay, where we say the amplifier is going to be governed by our this VB basically transconductance, which is going to be decide our transconductance value. Basically, it is how this transconductance is going to be depend. That is basically VB delivering. So if we translate this in this form, basically this is a replica, nothing but so we can design it like this also, where the Vin is given here and VB is on this one. This is a similar replica of each other. Okay. In order to alleviate the drawbacks of the telescopic cascode of op-amp, the primary advantage of folded structure lies in the choice of the voltage level, because it does not stack the cascode transistor on the top of the input device. That is basically advantage of that this folded cascode op-amp. And similarly, if we have a design like this one, we can replicate with this part only. So if we do so, it means we can design this thing also in the form of a folded cascode amplifier. So this is for nothing but this is for a this one part only. And if we have a folded cascode amplifier, then we can design this op-amp in this format on this one. For doing this thing, what are the advantages? What is the difference between the two circuits will be there? That in the figure A, one bias current ISS provides a drain current of the both input transistor and cascode device. In FB, figure B, the input pair requires an additional bias current, that is this one. That is what is the basic difference in between these two circuits. And in figure A, the input Con moment level cannot be exceeded above this value, whereas in the figure B, it cannot be less than this value. In figure B, it is possible to tie the N-well of the M1 and M2 to their common source point. For the figure B, we are saying this part, basically it is possible to tie the N-well of the M1, okay, this with M1 and M2 to their common source point. This is common source point. Okay. Now see, folded cascode op-amp with the cascode PMOS loads. This is what PMOS loads only. Only the PMOS is there. So in that case, maximum output voltage swing is there with the proper choice of the VB1 and VB2. VB1 and VB2. Peak to peak swing will going to go into this one for a one side. The swing is larger by overdrive of the tail current source in the telescopic cascode M5M and 6, M5M and 6 may require a high overdrive voltage of if their capacitance contribute to node X and Y is minimized. Now if you're going to one, since equivalent circuit the output shorted to the ground, this is that time we are going to get this thing. Since GM3 plus GMB3, it means parallel to the R03, it should be less than R01, R05. That time we're going to achieve the overall transconductance is going to be dependent on the basically M1 only. In that case only we are achieving the I out is equal to IT1. And for this type of circuit, what is going to happen? We achieve this thing. So thus overall, what are we going to get in? We are going to have this overall voltage going to come this thing by involving these two all parts. Okay. The gain is usually 2 or 3 times lower than the comparable telescope code. Now, folded cascode op-amp Effect of the device capacitance of the non-dominant pole in telescope and folded Coscote amplifier. What is going to happen? Basically, the pole at the folding point, that is the source of the M3 and M4, is quite closer to origin than associated with the source of the Coscote device in a telescope topology. So a high gain folded Coscote amplifier. This is the basic design for the high gain folded Coscote amplifier. For the case of that one, we achieve this part basically. The circuit provides a higher gain because of their greater mobility of NMOS device, but at the cost of a lowering at the pole at the folding point. That is the pole basically. Now, telescopic and folded cascode, what is that? We have already seen that the over voltage swing of a folded cascode op amp is only slightly higher than that of the telescopic configuration. This advantage comes at the cost of the higher power dissipation, voltage, lower voltage gain, lower pole frequency, and higher noises, where the folded cascode op amp are used quite widely, even more than the telescope topology, because the input and output can be sorted together and the choice of the input common mode level is easier. In telescope op-amp, three voltage must be defined carefully. That is the input common mode level and the gate bias voltage of the PMOS and the NMOS Coscode transistor, whereas in folded Coscode configuration, only the latter two are the critical. In a folded Coscode op-amp, the capability of handling input common mode level are close to the one of the supply rails, basically. Now, this is what the design of folded Coscode op-amp. So this is what we have already seen at the latter case. The same one of the example I've taken to design a folded Coscode op-amp. This is a practical value, and when we are assuming this part, we can achieve our folded Coscode op-amp. Basically, that is what I'm saying. This part is additional. Other things we have already seen. And this. So then we're going to see a power budget, output swing, W by L ratio, and the output common mode level. These are the calculation basically. I'm not going to look into that one. Then determining the W by L ratio, gain, and these all things. Now, Coscode op-amp with a single-ended output. Single ended, basically this thing, when we are not having in between a difference of the outputs. That time Vx is the VDD minus VGS5 minus VGS7. That is a limiting the maximum value of the output to the VDD minus VGS5 minus VGS7 minus VGS6, wasting one PMOS threshold voltage in the same. And in the figure P, to solve our issue, the M7 and M8 are biased at the edge of the triode region. What are the disadvantages for this doing this thing? It provide only a half of the output voltage thing. And the second is what? It contain a mirror pole at the node X, thus limiting the speed of the feedback system employing such as amplifier. It is preferable to use a differential topology, although it requires a feedback loop to define the output common mode level. This is a triple Coscode op-amp, where the triple Coscode topology provide a gain on an order of GM-R0 to the power 3 by 2, but further limit the output swing with the 6 overdrive voltage subtracted from a VDD in a circuit. It is difficult to operate the amplifier from a supply voltage or a lower while obtaining a reasonable output swing. This is nothing but triplet of that one Coscode op-amp. Now comes to the two-stage op-amp. So we have already seen now what is that is single stage op-amp. Now let's next study what we are just seeing about the swing. So now we'll see how this high swing will be achieved with the help of a two-stage amplifier. This is the basic block of that one, where the first stage is going to give you the high gain and second is going to give you a high swing basically. The first part is that the gain of the one state topology is limited to the input pair of the transconductance and the output impedance. Second, two-stage op-amp consists of the first state providing a high gain and the second providing a large swing. The first state incorporates various amplifier topology, but the second stage is typically configured as a simple common source stage to allow a maximum output swing. Basically, maximum output swing is going to be achieved by the simple common source stage. So now the question arises here that can we cascade more than two stages to achieve a higher gain? Is it that or no? Each gain stage included at least one pole in the open loop transfer function, making it difficult to guarantee stability in the feedback system using such an op-amp. For this reason, op-amp having more than two stages are rarely used. That is why we basically when we are utilizing op-amp in a daily user, we won't prefer to use this thing. Now, simple implementation of two-stage op-amp. Okay. Now see here, two-stage output 1 and output 2. This is what where the AV, that is voltage gain at the first stage, is going to come when you are going to calculate the value is going to come like this one, and for the case of second stage you will get this one. So basically, if I'm going to say for the first state only M1, M2 and M3, M4 is going to be considered for the case of stage 1. You can see it here in this one. That is, this part is going to be considered for the case of the first state. For the case of second state, it is going to have a this outer one going to give you basically the second stage. Basically from here, this is the first stage and second is this one. Now the overall gain, you can say multiplying both will going to give this one. In this case, we are achieving the output thing going from a VDD minus VOD 5,6 minus VOD 7,8. VOD means overdrive voltage. Two-stage op-amp employing cascade to obtain a higher, the first stage incorporate cascade device. The overall voltage gain is going to become like this one. When in the case of, we have already seen this one, what we have seen here, we were utilizing for the first case here. Now we are saying that we are cascading it. Here we basically cascading. This is what we are cascading, and that case overall voltage gain going to become this one. Cascading we have already seen in the previous slides. So that is what the case of the cascading. Now two-stage op-amp with a single-ended output will going to be have single-ended. We are not taking here. We are taking only here. Although it is a two-stage, because the first stage is going to become from here there, and the second is from the outer one. Note that if the gate M1 is shorted to output, M1 is shorted to the output to form a unity buffer, the minimum allowable output level is equal to VGS 1 minus 1 ISS, VISS. Okay, that is at this point. Severely limit the output swing. This is what going to happen when we are going to talk about the unity gain. Due to that one, that is why gain boosting will be there, the increasing the output impedance by feedback. Our out will be going to come like that, where the M1 operates as a degeneration register, which basically This is behaving like a degeneration. Degeneration basically always going to you can say advance or gain. Means advance or gain. You can say there's a negative feedbacking is there when we are going to talk about the degeneration register. The voltage variation at the drain of the M2 affect at Vx to a lesser extent because even regulate this voltage, that is nothing but Vx is equal to Vb with a small variation at the x, the current through the R01 and the hence the output current remains more constant, yielding a higher output impedance. Okay. In that case, R out going to become to be A1, GM2, R2, R02, R01. R2 is booted substantially with the stacking more Coscode device on the top of the M2. Now we are just talking about now gain boosting in the Coscode stages. For a small signal operation, VB is set to be 0. In that case, what is going to happen basically? Then is going to come and the minimum output swing will be there since Vx is equal to VGS3 and the minimum value of V out is VOD2 plus VGS3. The auxiliary amplifier limit the output swing and this will be going to be give you minimum output swing. Now boosting output impedance of the differential Coscode stages. This is all how we basically do a boosting. There will be a different circuits. I have shown it here. And for the folded Coscode circuit you used as an auxiliary amplifier. Now gain boosting applied to the both signal path and the load devices. This is basically a structure. We'll look into that one. Not go into detail of that one. Now comes to the comparison of performance of various op-amp topology is going to become like this one. For the case of telescopic folded cascade and a two-stage and gain boosted, what is we have seen that in the case of telescope, in comparing all thing that one, we are achieving a medium for the output swing and the highest in this one. But in the case of power dissipation, we are getting this thing low and low for the telescopic. Okay. In the telescope, basically, we are not achieving a unity gain thing. We are not achieving a properly. So if you see telescopic to folded cascade, we are advances that thing that is in the we are achieving the medium and a medium, and we as well we are achieving the unity gain as well. Now comes to the two stage. What is going to benefit in that one? We are achieving a gain also high, output single is the high, but what does that happen? That speed is going to become low, and the power dissipation is also medium, and this will become a low. Now within that one, if we apply a gain boosted thing, then that time we achieve a very perfect result. That is the high gain, medium output swing, and medium speed, not the high, but the medium, which is a very good thing. And but the high power dissipation is there. That is one of the things is there. Now comes to the common mode feedback. That is full differential circuit have many disadvantage over their single-ended counterparts such as a greater output swing, avoid mirror poles, higher closed loop speed. However, the high gain differential circuit require a common mode feedback. So basically, simple differential amplifier. If I'm going to see into this one, this is nothing but that one. Okay, so if we make this circuit, it is going to be similar like this one. If we do so, if we are going to feedback that one, okay, we'll achieve this part, common one feedback. So high gain differential pair with the input shorted to the output. So what is the common mode level at the node X and Y? common mode means this part and this part. Since each of the input transistor carries the current ISS by 2, the common mode level depends on the how close ID3 and ID4 are to this well. The effect of the current mismatches and mismatches in the PMOS and NMOS current mirror defining ISS and ID3 creates a finite error between the ID3 and ISS by 2. If ID3 I4 is greater than the ISS by 2, then both M3 and M4 must enter the triode region so that their drain current falls to ISS by 2. Conversely, if the D3 4 is less than this ISS by 2, then both Vx and Vy must be dropped so that M5 enter the triode region, thereby producing only 2 D3, 2 ID3, D4. For that case, simplified model of the high gain amplifier going to be comes like this one, and which is having a similar advantages for that one, since the current error depend on the mismatch of and RP parallel Rn is quite high, the voltage error may be large, thus driving a p-type and n-type current source into a triode region. As a general rule, if the output common mode level cannot be determined by the visual inspection and require a calculation based on a device property, then it is properly defined. In the case of high gain amplifier, the output common mode level is quite sensitive to device property and mismatch, and it can be stabilized by means of differential feedback. Thus, a common mode feedback network must be added to sense and common mode level of the two output, and accordingly just adjust one of the bias current amplifier. This is the what now. This is the concept behind the topology of common mode feedback. This is what the basically you need to understand how we basically mean. So this is what the last PPT, and this is now here the our basically first unit is going to be complete here. So this is all about that first unit, that is including all the part that is basically a differential amplifier, that is a single ended and a differential operation, then basic differential ampere that is having a quantitative and qualitative analysis, and then we have seen the current mirrors and references basically, then we have seen that voltage and current references, and then op-amp amplifiers. Basically we have gone through the one state op-amp and the two state op-amp, and as well as we have gone through the process parameters. This is all about the first unit. So along this one, what we are going to see, there are some I'm going to even going to share this PPT also with you. We're having a several question numericals based on this one, unit 1, which I've covered up. If I'm going to look into the first question here, that is here. Our first question, that is the constant current source using a two matched NPN transistor with the beta 100. Since I have taken from some of the book, so I have taken out that from that book only. So this is here the question is given where it is saying that the VB is 0.6 is shown, and calculate the I out. Basically, this is nothing but a current mirror. Okay, if we are able to find out the current through this region or this region, we are able to find out the V out. So if we going to apply a KVL across this one, okay. So what is that? IREF. Basically, this is nothing but a IREF, the reference current, that is a VCC minus VBE. That is a VCC minus VBE. If I say this is the IREF, that is IREF is going to come. What is that? IREF is equal to VCC. That is a VCC. That is minus, what is that? The current across this one, VBE. Okay, VBE. And what is the resistance behind that one? That is this one, that is R. So if I'm going to evaluate that part, that is nothing but that is written here. If we do so, we'll get this value that is coming to be 1.9 milliampere. Okay, but what is going to happen? Our I out is not exactly same for the case of this figure. So we need to check what is the beta value. Beta value is not given, means it is not very high, it is saying. So it means we need to check about this value. So if I'm going to evaluate that part, we're going to achieve this value, that is 1.86 milliampere. Similarly, if you want to look into that another question, so it is a similar type of a question where you can see the current mirror has been used, and if we evaluate the same way, we will get the value for the R1. Okay, so this is also going to define you that one of the question on the based on the current mirrors. Since as you can see it here, assuming that beta is 150, okay, so the current across this one, is nothing but a beta by beta plus this one. So as we know already, IREF by applying a KVL across this one, okay, we can achieve. If we do so, we already know that current. This is saying that providing a 1.5 milliampere. It means we already know that current that is nothing but IC2. Okay, so IC2 is already given, and if you are going to evaluate this thing, and we'll on the basis of that one, we'll get a value of the R1. So this question also having a one kind of a this uh, basis that you can, if you're going to see it into that one, if you want to have a current, if we are giving a current in the milliampere, and if you want to current in the microampere, in that case also we require a higher resistance. Since if we are going to increase this current, this basically resistance, then only we can achieve that. If I'm saying that we are giving a IREF in the terms of the milliamps, okay, and if you want the current in the terms of a microamp, okay, in that case what we can see from the figure, this particular equation, we need to have a very high resistance. Okay, so in that case we require that converted one of that current mirror we utilize, that is a Vidlar current mirror, basically it's going to swing to that one. That is advantages where we basically do a resistance over here, sorry, not resistance here basically apply. So that is a basically advantages. So this is what the basic behind this one. So now comes to the differential pair of that one. So here the several questions have been given, you can look into that one. Now already that given part is that, so what we need to do, what we need to find out, we need to find out the value of differential gain. Okay, so we know already the formula for that one, that is V2 IE 2 IE basically across this part. Okay, that is nothing but a VEE minus VBE, okay, across this part, VBE VBE, okay, by RE. Okay, this is what the part. So where all these values have been already given, if it is so, we can able to find out the IE current. Okay, now the differential mode voltage is given like VD, then we already know that RE is nothing but a VT by IE. So RE we can get it. So differential mode gain is nothing but RC by RE. So since the RC is already given 1.8 kilo ohm, and we have find out the RE value. And if we equate that one, we can get the value that is nothing but the 80. This is the answer. For the case of this one, it is going to have this value. So these type of different questions I have given over here. You can go into that one and practice it, because definitely I'm going to ask you the several questions from this part, including the op-amp and all. Even some of the question I'm going to further going to give you on the basis of the op-amps. So these are the questions. So now the first unit is going to be completed here now, including all the things. From the next lecture, I'm going to take up the next unit. So basically that also required two lectures of the 2 hours. Basically, then it was going to complete that our task of the 2 unit and a midterm also. I'm planning to have your midterm from the 2 units, involving all 2 units only. Okay. So this is all about the 1 unit. If you have any kind of a question, then ask me. Otherwise, I'm going to hang up. Yeah, class, am I audible? And if there is any kind of a question, then ask me. Otherwise, I'm going to hang up now. So I'm assuming that nobody having any kind of a question. So one question I'm having, Shivam, am I audible? Priya, Shivam, Ankit Kumar.